Just need to find my mouse cursor here, and
All right, go ahead.
all right. Before I get started, I want to
just click hide on this thing.
Oh yeah. Where's my mouse pointer? I probably have to do this, and then do this, and then do this, and now
Awesome.
Are we good now?
Yes.
Amazing.
Wait, it's time.
Nice. Okay. Before I get started, I want to ask like a slightly different version of the question that Rob asked earlier, which is who here has like started learning to program but isn't doing it like as their career yet? Like raise your hand if that. Okay, that's maybe less than half. Well, I hope the talk is still interesting for those of you who don't fit that category, but I think it's mostly for the people who are still kind of new and like trying to figure out like how to get from learning stuff to like being somebody who can get paid to do this. About me, I work for Axiom. We also do observability, mostly for smaller clients than Dynatrace. I also work on some open source stuff, so Create T3 app, TRPC, and I've contributed to like some of the problems or projects in freeCodeCamp. And like most days I work on this application. So you have a bunch of your logs, and you can query them, and you can get like these charts, and you can see the data, and you can build these dashboards. And the crazy thing about this is that like this is my job now. Like that still feels very strange. The reason is that like I'd always kind of been interested in programming, but I only really started doing it like in March of 2021. And like a year and a half later, I got my first job, like getting paid to do this full time. And in that time, like I spent a lot of time on Discord and other places where kind of people who are also trying to get there gather. And I think I kind of figured out some patterns of like what the people do who end up making it. So that's what I want to talk about today. Yeah, so the main thing is just building stuff a ton, build a ton of stuff, like always build projects all the time, never stop building. Thanks, that was the talk. But seriously, I think especially kind of people who came from university have this like model of how learning works that doesn't really work for programming. So a circle maybe isn't the best way to represent time, but like if you imagine like you're doing input, 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 so that's like doing a course or reading or something, watching YouTube tutorials, and people think like you keep doing that, and at some point you know enough to like output code or an application or something. That's not how it works at all. The way it works is this: you front load like the bare minimum of knowledge that you need, And then you start building stuff, and you go back to input, like to figure out how to solve a problem that you have. And like this is, I think, really the fundamental difference that helps you get to the point where you can do this for a living. And I want to just show a couple of things I built while I was getting ready to get my first job. So this is the first website I ever put on the internet, and it's not even really on the internet, it's in a code pen. But the point here is like, no matter how early it is, like start putting stuff out there, like build stuff, put it on the internet, can be a website, can be an application, whatever. Like, I think people are very scared that they don't know enough technologies yet, right? Like you don't know React, so you can't build, like, no, if you know HTML, you can put a website on the internet. And then you learn another thing and you can put a better website on the internet. And then like you learn a bit of JavaScript, you can put an even better website on the internet. And that's kind of how the whole thing works. Especially if you're doing these courses, like don't just pass the test. And I think this is especially a trap in freeCodeCamp because they have, to anybody who doesn't do it, they basically have like automated, I don't know, Playwright or something tests where tests like the website needs to have a div with an H1 in it that says, welcome to my website or something, right? Like that's how they test that you get the certificate or not. But I think where you really learn is when like you try to solve problems. So this is like a really silly example, but like I was reading these magazines that are basically like catalogs, and I like the layout. So I tried to like replicate this with a grid. And this was like a couple of days into doing CSS. And it took me the whole evening to figure out like how to get this working. And I think this sort of stuff is like where the real learning happens, when like you care about solving a problem, not when somebody tells you like, here's your assignment. Especially to those of you who are really early, like this is maybe the most important thing, like learn Git, learn GitHub. You don't have to really learn it. You just have to learn it enough to be able to get your code on there, basically. If you want to show things to people, like they have to exist on the internet. So like GitHub is the place where code exists on the internet, so that's where you should put it. And not just that, but realistically, like once you put the funny thing is you have to put the code up, but nobody's actually going to look at it. Like they're not really going to read it. So what you should do is have a really nice README with each project and have screenshots of the project, maybe like a video. If you're already at a point where like you can get your app deployed onto a real server somewhere, like do that and have a link that people can click on to use it. Yeah, this is super important because I think especially when you're self-taught, the only way people can like figure out if you're good or not is by looking at the stuff that you've made. Next big thing is build real things for real people. I was working as a university lecturer back when I decided on this career change, and we were using this platform. It's called, I think, Doodle or Noodle or something, where like people can register for slots of like teacher time or events or something. And then they stopped being GDPR compliant, and the university said, right, we can't use this anymore. So I built, and back then this was only in Django. There's no JavaScript happening here. This is all coming from the server because I didn't know how to do anything else. I built this thing where it's like that thing. I can make events, and then people can write their name into slots, basically. And then I sent that to people to register, and they said, like, hey, it kind of breaks when I do this. And then I fixed that. And like in a couple of cycles of that, I really learned a lot, and it started becoming like kind of a real app. I mean, I think when you look at the screenshots, you can still tell that this is like not a real app made by a company, but it started becoming like a thing that people could use. Another example is I made this thing for language learners. So if you're learning languages, like one of the hard things to figure out is like which words to learn. And so either you can like go through a list of the top 2,000 words and learn that top to bottom, which is kind of bad because like starting at word 500, you're not going to use all of those or come across all of those. Or people like just learn the words that they see, but then like you might see that word only once, and then you've wasted like a word in your brain. So I built this thing where people can put in all the words that they've seen, then it compares it like against frequency lists of how often words are used in, I think it was Netflix and a few other things. And like 10 people or like 15 people still use this every day. And like it's a really simple app, but just getting the feedback from people and like figuring out what people don't like and improving it. This feedback loop is super valuable. However, if you don't know what to build, my recommendation would be build Twitter. Twitter is like the greatest thing to clone in the world because it exists at like every level of complexity, right? Like at the simplest version, I don't know, you build the login page. Then you like make it so people can post a tweet and other people can see it. Then you make it so there's likes and retweets and reply threads, and Twitter also has like voice chats and streaming videos. So like by the time you've built all of Twitter, you know how web dev works. You know how like all of web dev works. So like you can basically build Twitter at every skill level, and there's always going to be like a next thing that you can learn. This is super important. Don't worry about writing good code. Write the worst code in the world. It doesn't matter. You have to write like a million billion lines of terrible code until you ever write one line of good code. So just get the code out. Let's see. I hope this doesn't break the screen share. But anyway, this project was like, when you have the dock open on the Mac, there's a bunch of wasted space to the left and the right. So I thought, like, what if you put little apps there? So I put like a notes app and like a weather app. And I just quickly, this is the only code I'm going to show because I think like it's not really about code. But let's see. Here, we're using TypeScript, but we're getting DOM elements, and then we're just saying, oh, yeah. Like we're just saying what they are, even though we don't know it. There's like 15 document query selectors here. This function is great. So I have this variable called D, which I guess stands for date. Then H, which I think it might have been for hours. And then E, like I've read the function 3 times before giving this talk. I still don't know what E was meant to mean. But it doesn't matter, right? Because I built a thing, and that's in the end the only important thing. So like, write terrible code, just ship projects. And until now, I've kind of been talking about like stuff that I think I vaguely did right. Here's something I did terribly wrong. So for anybody who doesn't know, this is a GitHub contribution graph. So the more green a square is, the more code I wrote that day, roughly. And you can see there's kind of like a big 2-month-sized empty spot here in the middle. What happened was I knew how backend code worked. I knew how to send HTML to the front end. I didn't know JavaScript. I didn't know React. I didn't know how databases work. I didn't know how to get my app like onto a real server. I didn't know how Docker works. So I thought, right, I'm going to learn all of these things and built the greatest app, or like the greatest app for me. And so I just started doing tutorials. And by the time like I'd done the second or third course, like I'd forgotten everything from the first course. And yeah, this is what this whole looked like. I just kept doing more courses and like getting more worried that like I didn't know how, like at the end of the thing, I didn't know how to do any of it. Here you can see some courses I bought on Udemy, and I think I finished one of these. So my solution would be build something after every course, or if the course is really long, then like build 3 things throughout the course, like take breaks. I think you can get a job of like 3 courses if they're the right ones. So yeah, just, I know I'm saying this a lot, but just build stuff, guys. Another way of avoiding this tutorial hell thing is for every project, like add between 0 and 1 new technology. So like don't add 5. So I don't know how well you can see this here, but each column is a project I did, and it's not all of them, but whatever. And each row is a technology. And the point is like, it's not very green at the left side, it's very green at the right side. So like, they just get added slowly. And every time, like once you've used something in 2 or 3 projects, you're so comfortable with it that you like can just basically use it anywhere. And you're never going to learn anything 100%, or you should not try to learn anything 100%, because I don't even know 100% of HTML yet. But like you get to that point where you kind of know just barely enough to like not have to make it your learning focus for the next project, I would say. Important one, it's okay to give up. Especially if like you've set your goals a bit too high, like just throw the project away, it doesn't matter, start a new one. Or what you can do, what I think is even better, is like get to some artifact. So maybe you had this idea of like a really cool full stack project, but turns out you're still like 3 technologies away from being able to build it. Maybe you just build the UI for it and take screenshots and put them on GitHub, or like whatever, like figure out some way to bail out, but still have something to show for it, kind of. Yeah, going deep occasionally. Here I went deep on CSS. I did this for basically every technology at some point where like I stopped doing any other stuff. So like only backend or only CSS or only JavaScript. But CSS is the easiest one to show because like it's screenshots. So with these ones, like I tried to build these realistic looking things, so like a calculator and a drum machine. And I've not built anything that looks like that since then. But just in like fighting against CSS and how it works, like this was kind of the step where I became comfortable with CSS basically. And I had similar like 1 or 2 week long like deep dives on basically everything that I know how to do now. Also go on side quests. So this is a Discord bot I've built. I've never built a Discord bot since. I'm never going to build a Discord bot again, most likely. I don't really go on Discord that much. But I had some friends who were doing like a challenge and they were using Discord to log their progress. And they were just posting like, I'm at number 39. And so I thought like, hey, every app is like saying, check off, like it's a to-do app, right? I can build that. I just don't know how to do the Discord part. So I learned how to do that and then I did it. And I think with like every new thing that you learn, like learning the next thing becomes a little bit easier. And so once you've learned like 20 things or 100 things or whatever the number is, like you can basically learn anything to a certain level without too much difficulty. I think we're kind of getting closer to like the being job ready part now. A really big thing for me is like build something that is convincing as a real application at some point. So like when you do your first little projects and like you compare them to real websites or to real apps, they're not going to look like that thing. They're going to look like kind of like a crappy baby version of that thing. And that's okay because like we all start there. But at some point, like whether it's like, for example, make a UI that looks like it could be a real app, or if it's not about UIs, like make a form that handles like a failed fetch the way a real app would. Like figure out a couple of things in whatever project you're doing and like get them as good as the apps that you're using on your computer or your phone, basically. And everything around it can still be like held together with glue and duct tape and paper mache, as long as you have like a couple of things where you've really put in the effort to, yeah, make them kind of real, I guess. And that brings me to what good final portfolio projects are. Final portfolio project needs 3 things: a front end, a back end, and a server. If you're self-taught, you're going to get hired most likely as a full stack web developer, like unless you're, I don't know, if you're learning embedded computing or something, like don't listen to anything I say, I guess. But if you're learning web, every company wants somebody who maybe specializes in one of these things, but can kind of do all of them a little bit. Because like, you can't build a front end without knowing how the back end works and how the database works. So yeah, that's the most important thing for projects to have. The second most important thing for projects to have is, and I've said this before, they need to be on GitHub. They need to have a README, like, and don't just write like what the project is and put screenshots. If you're doing this thing I said, where you build like a couple of really of things where you really challenge yourself, like write what those things are. Here's a data point. I had about 10 interviews or interviews with 10 companies before I got my offers and then picked one of them and get a job. This site, which was like my main project in my portfolio, had 4 user accounts by the end of those 10 interviews, other than the accounts I'd made for myself. So, and in fact, the company that hired me, nobody from that company had registered an account, which I knew because the email addresses were in the database. People don't, like, not only do they not read your code, they also don't register for your application. So like you need to have the READMEs, you need to have the screenshots, you need to have videos, whatever. Like convince people that you're really doing this to the point where they believe you without even kind of checking, if that makes sense. One big thing is, I think like open source is something that people are really scared of. It's not like, I guess whether it's scary depends on if you find it scary or not, but it shouldn't be scary. Here's my first PR that I ever got merged into an open source project from freeCodeCamp, actually. So one of the demo projects, it wouldn't deploy to Heroku. Heroku, for those of you who are newer, is a platform people used to deploy apps to and don't anymore. The reason it wouldn't deploy is because like the app was hard-coded to run on port 3000, but on Heroku, Heroku decided what port your app runs on by injecting an environment variable. And so the only change I made was instead of just having the number 3000, I don't think I can zoom in on this, but you'll have to believe me, except for having the number 3000 there, I said, use the environment variable, and if we don't have that, then use the number 3000. And I was super nervous. CI was running oh my God, is it gonna go green? No, it went red. My code was formatted wrong. I pushed again, it went green. It's the most heart-wrenching thing the first time you're doing it. But then you get it merged, and yeah, or maybe you don't get it merged, that's also fine. But it shouldn't be that scary, basically. Last big thing, and this goes back to you need to always be building, is if you're learning how to become a web developer at home on your computer, you have to put the hours in. You're up against people who've gone to university for this. You're up against people for the same jobs who've already had a job. It takes a lot of hours and a lot of work and a lot of projects to get to the point where you are. I think there's a couple of people, especially on YouTube, who are oh, get your developer job in 3 months. Maybe that's work for somebody, I don't know. I think I got mine way faster than most people. But even then, it was 18 months of making a lot of sacrifices. And finally, I hope I'm still on the Wi-Fi. I have the portfolio. It's not the one that I sent when I got the first job, but I think the only difference is that I added the line of the company that I work for. And so, yeah, all I had was 3 sentences about myself, contact page with my email, GitHub, and Discord, a blog with 3 terrible posts that I think nobody ever read, and my projects, which they all have a screenshot. They all say which technologies there are, so TypeScript, Next.js, and so on. They all link to GitHub, and they all link to a live demo. I think I know I've said this 5 times now, but this is what you need to do. You need to have the screenshots, you need to have the text, you need to say what you use, and you just need to make it really easy for people to know that you've done a really cool thing. And yeah, I think that's all I had. So thanks for listening.
Questions?
First.
What were you doing before you started coding?
I was a university lecturer at an art school.
Art school?
Yeah.
And did you have any, so you said you started to code a little bit beforehand, always how's your affinity to the logical? So when you say art school, it's more of a creative process, and how is your connection to
so I was really into computers and programming when I was a kid. I learned C, because that was a language we learned back then when I was in, I think 9th grade or something. But then I had a terrible teacher who convinced me that I was no good at this and I was never going to make it. And so I went and did something else. And 10 years later, I came back and figured out hey, maybe that guy still thinks that being a mostly front-end web developer isn't real programming, but the job is real. You had a question?
Yeah, I was wondering, what is your main motivation to code? Or what was your main motivation to,
At the beginning, it was, I think 2 things. Number one, I was really miserable in my old career. And I thought hey, I basically took inventory of my life and looked at what else I could do where within a reasonable amount of time frame, I could have a new career. And at first, I'll be very honest, my motivation for doing this was I wanted to make more money and have a job with more freedom. Over time, I found ways to make it really fun for myself. And now I'm one of those guys who codes after work. So yeah, I think it's totally okay to get into it for the money, but you have to find a way to enjoy it, because otherwise you're not going to be able to put the hours in. Yeah?
You mentioned sacrifices. Can you elaborate a bit on that, on how you managed your old career and learning? And
yes, so I think I got quite lucky. It was in the middle of COVID, and I think companies are very tolerant, let's say, of people working a bit less than before. So I was still working maybe 20, 30 hours a week, but not 40. I also had a daughter. So the sacrifice I made basically was I didn't see friends as much as I used to. I dropped every other hobby I had. I would say I was learning to code between 4 and 6 hours a day on average. Like that's the basically I wake up in the morning, like do it for 2 hours, then my daughter would wake up, then I had like a day of work, pick my daughter up again, she goes to sleep, do 2 more hours. Sometimes I got a little bit in the middle, but like, yeah, it takes a certain number of hours to get good at this. It's probably a different number for everybody else, and I don't even know what getting good at this really means, but either way, like it's a lot of hours to get to the point where a company will hire you, and you just have to find them somewhere. We're all in different situations. It's not necessarily fair that different people have more time than other people, but yeah, you have to find the time somewhere.
Did you mainly follow FCC tutorials and program, or how did you?
Mostly. So I started with freeCodeCamp until I got to their React course, which is terrible. It might have changed by now, but back then, like hooks had just come out and functional components, and they were still teaching the old stuff. And I think they still are actually, just because like nobody's updated it. So at that point, what I did was I found an amazing teacher on YouTube, Jack Harrington. Look him up. He has like, I'll come talk to me later.
Okay.
He has an amazing series of videos on both React and also on TypeScript. And then I went back and did the freeCodeCamp projects, because I think like what's really good about freeCodeCamp is that they make you like do projects, and they have tests to make sure that you actually did the projects. Like the courses themselves, I mean, like the React one is particularly bad. I think the other ones are mostly like okay, but none of them like give you enough knowledge to be able to like do all of the stuff afterwards, I think. And funny enough, like that's actually good, because it means like you have to learn how to Google for stuff and how to go on Stack Overflow and how to read documentation. So yeah, I would say freeCodeCamp is fantastic, but at some point you're going to need supplementary material most likely. Yeah.
My question is, what has been your biggest challenge that you have like faced on?
I think the hardest thing actually was, I mean, while learning, I think the hardest challenge was like getting out of tutorial hell. That was, you saw it took me 2 months. Since I started working, I think the most difficult thing at first was that working like at a company on a team is so different from building your own projects.
Maybe I can also comment the learning. So even though there's so much learning to get to the point of getting a job, it's actually almost paradoxical, the fact that you can almost never on your own, until you get a job, learn as much as you will do in the first 3 months on your job. Because you're putting in 40-hour work weeks, learning on the job. And for me, that was like, wow, I'm getting paid to learn. Like, this is amazing.
Yeah.
So, yeah.
And like the code base you're going to come into at work, like number one, it's probably going to be kind of bad, because like every large code base is kind of bad. But also like you're going to spend more time reading code than writing code, which is a very big change from what's happening when you're building your projects. And like learning how to read code, like you get some ticket that says like, right, when the user clicks this button, the wrong thing happens. Like figuring out how to fix that in a code base that's probably like across 3 services and I don't know, 1 million lines or whatever. Like this is a whole different category of learning. So like as soon as you're in your first job, yeah, it's just a very different thing from when you're building these projects. This is also why I would really recommend like doing at least a tiny bit of open source work before you get a job, like if at all possible, because they're also like, you have to read other people's code and like figure out. Basically, I would say the trick is like to learn to ignore 99% of the code and like only find the parts that are relevant to what you need to do. But that's not an easy skill at first. Yeah?
Yeah, so first, congrats on the journey. It's a great one. So my question is, if you would do it again, like, is there something that you would do other than, of course, build a project, like something that when you got to your job, you said, oh, maybe I should have done this.
Mm-hmm.
Punch that teacher in the face.
I think there's kind of a lot of stuff that I didn't know and that was new when I got the job, but I don't think like I would go back and like learn it up front, because I don't know. It's hard to say, right? Because I can't compare like my path to a different path that I've not done. I think the big one is never get stuck for 2 months and like notice when you're stuck, basically, because I didn't realize it for the first, I don't know, 4 or 5 weeks. And those 2 months were like just completely wasted time. Other than that, honestly, like build, solve problems, find people to talk to, either like here in like Meet Space or online on the internet, who are maybe like at the same level you are or like 3 months ahead of you. That's like the perfect person you need to talk to. Because somebody who's like a senior engineer at whatever company, like they don't know anymore like what you're going through. Like that's so far removed for them. Whereas somebody who's like 3 months ahead of you, like they just made a bunch of mistakes and they're going to be able to tell you like how to do it different and better.
To what Sebastian said as well, for me it really also helped to have the meetup group as accountability.
Yeah.
So I was thinking, oh shit, I'm going to be at the meetup in 1 week. I don't want to tell them I'm stuck in the same portfolio project. So maybe I should make some progress. So that can help me to kick my own ass.
For me, it was my partner saying, like, you've been learning this for 6 months now. Like, what's going on? Why are you on the computer every day?
Yeah.
But yeah, accountability and finding ways to just do it. Yeah.
Maybe one last question, and then I'm sure Christopher will be free to answer questions afterwards.
So yeah, technology-wise, like with your experience now, like having a job and stuff, what would you like suggest learning now for like an inspiring web developer, front-end developer?
I would say
technologies?
2 things.
Yeah.
The first one is it doesn't matter. As long as you build stuff, like it doesn't matter if it's like server rendered HTML from a Django app or Rails app, or if it's like React or Angular or whatever. Once you've learned like your first 2 or 3 technologies, like learning the next one becomes way easier. So just pick one and build projects. That being said, if you're gonna pick whatever the most popular thing is, honestly. And currently that's JavaScript with React and Node. That's like, it's the easy, I think it's not the easiest stack to learn, but it's the easiest stack to learn technologies that like a lot of companies are hiring for.
Thanks again.
I hope it will be okay now.
It's working. Woo!
Great. So, yep. Let me introduce myself. My name is Yuri Khabarov, and I do some software stuff for 10 years, I guess. So, and I want to tell you a little bit about my occasional research that I did randomly one day. So, I hope that all of you know a problem called FizzBuzz. So, description is, you have a range of number from 1 to n, and you just need to iterate through every number. And if this number divisible for 3, you need to write a fizz. If this number is divisible to 5, you need to write a buzz. And if number is divisible both for 3 and 5, you need to write a FizzBuzz. Otherwise, you just need to write a whole number. So one day I was sitting on a network for technical coworkers called Blind, and I just randomly typed FizzBuzz word in search bar. And I got some few interesting results in the posts. So it was looking that somebody has been asked by Google to write a FizzBuzz on the interview. So Google is a well-known company for having really difficult for solving problems, typically. And I went to the most interesting part of every post on the internet. I went to the comments. And there were a lot of just usual jokes, but I found one very interesting comment. So a man who wrote this comment told that, you know, usually we check in for if number is divisible for some number, we use some division operation. But in this case, you can just write this one using counters just to avoid division operation, because division operation is typically difficult for our processors. And addition operations is really easy for them. And I thought that, okay, in this case, I can try it. I can just check it. And I need to realize that, of course, addition solution using addition will be more faster than division. So I usually do my job in Java, and I just wrote a really simple program using Java language and started to check in boundaries from 1 to 15 million. As you can see, I was just writing something to standard output and printing some numbers, and I just had encouraging results. It took about 64 seconds. It was much more than I expected, and I just implemented another solution, and I was using counters. So you can see there are no division operations at this code, and it was even slower. I was quite confused a little bit, so probably I need to do some code optimizations. So what I was thinking about, first of all, I was thinking about changing output way for my program, because we know that standard output is the slowest way to put the data. The second one, I was thinking about changing an algorithm of my program, because probably we can use some hacks, we can use some other ways to perform a division operation. And the third one, it was the main point, I didn't want to perform any pattern hacks. So as you can see at FizzBuzz, every 15 numbers, your pattern will be repeated. But I really wanted to measure arithmetic operations like division and addition in my CPU. So I decided to avoid that. And you can see small asterisks in the right bottom corner. I realized that my program will be faster, but results should be representative. So I decided to upscale boundaries up to 100 million of numbers. So what's regarding writing to files? So first one, my initial implementation was using standard output, but it took about 64 seconds. When I decided to write into the file, but not to standard output, it took me 10 times less. But when I decided not to write anywhere, just to keep results in memory, it was twice more faster. So currently, we're living in 2023. We have a lot of memory in our computer, so why not to use our memory? Another one is about algorithm. So to be honest, I'm not hardware guy, but my father is. So I called him via Skype and asked him, probably you know any ways how we can avoid this operand to get in a remainder. And he told me that, yeah, you can use some loops, bit manipulations, and subtractions. But and as you can see, I just replaced these division operations just with 2 functions, especially for 3 and the 5. Of course, I failed that. So I didn't achieve any good results. And it's easy to explain, because when you, for example, compile your code in Java language, and you will just use command java p to decompile this code, you can see that using new solution, we need to execute more operations inside of our JVM. And if we will do the same one, for example, with C language, and you will try to disassemble this program, we will see the same one. So, okay, I really tried to optimize it more, and I was trying to find any way. And first of all, of course, I decided to use a C language because it's more native, it's well-known, and I guess it will really give me a nice performance. Another one, it was really important that I need to measure business logic time precisely, so just avoid measuring time with memory allocations and other stuff, because we are really talking about arithmetic operations inside of our CPU. And the third one, during the implementation, I found that some functions are really expensive to execute, so I decided not to use them. But anyway, finally, as I said, we're living in 2023, 2024 is coming, and our processors in our computers typically multi-core, so we can use all of these cores just to parallel our stuff. First of all, it's about multi-threading. So if you have a big range of numbers, for example, from 1 to 100 million, I guess we can just divide these arithmetic operations to many threads to do the same work. The second point is, so if you will start with writing in C language, it's easy for understanding currently. So you can see it's like the same functions, the same implementation. So we just starting with some boundaries, checking for if number is divisible for 3 and 5, and just printing something to standard output. But we want to avoid standard output, so we will pass our results in memory. It's kind of like tricky if you're not familiar with C language, but let me explain a little bit. So you have a big array in your memory where you can just hold all your results, and you need to allocate memory for every element, and after that to print your data in this element. So it was one of the problem in future, and also you can see that there is a malloc function in C. So malloc function is just C function typically used for memory allocation. And if you're going through 100 million numbers, we need to perform 100 million allocations. But that's a big problem for us because memory allocation is quite expensive stuff for our computer, and we need to avoid that. So how does it work? So we have one big array for 100 million elements. It's quite huge. But we have a lot of memory, and we can just use it. And we need to allocate for every element. So first one, for another one, the third one. So that's why we need to allocate memory for every element in this array. It's quite expensive. Second problem was sprintf. If you ever tried to write your own function which will transform just integer type to string type, for example, you just need to transform number to string, it will be quite tricky. So the same one for sprintf, and it's a good function to transform your numbers or something like that. But if you will use also the code every time, it also will be around 100 million calls. So I decided to replace any number just by some constant string, or probably some letter, for example, because we know that this algorithm is right. And we are talking about measuring arithmetic operations in CPU, not about printing somewhere. We're not talking about standard output or any output, okay? So I decided just to allocate only once, just 4 arrays. 4 array for FizzBuzz string, 1 array for Fizz string, third for Buzz string, and fourth one, the last one, was only about X letter. So I decided that in this way, we can just assign these pointers of these strings to our output array. So as a result, our function became really small and elegant. So I did all this optimization, and I was thinking like, this true man from comment from the internet post was absolutely right, and I will achieve nice performance with counters against naive implementation with division. So I ran the stuff on my laptop, which just MacBook Pro with Apple Silicon processor, and I was quite surprised about that, because even after all of these optimizations, it took about around 100 milliseconds naive implementation with division was faster than counters. And I was quite surprisingly with that. Hopefully, I found a second laptop on my desk. It was the same MacBook Pro, but with Intel processor, so with previous generation. And I thought that I can do the same stuff on this laptop because, you know, typically Apple Silicon and Intel processors have different architectures. So what's Apple Silicon, you use ARM, and Intel has well-known old-fashioned x86. So I ran it on my Intel processor, and I was quite surprised because in this way, solution with counters was faster than solution with division. It means it was mind-blowing for me. So I tried to understand how does it work. So for further discussion, I guess we need to go deeper, and we need to firstly understand how a program works with our computer. So first of all, you have some code file with source code in high-level language, for example, C. And after that, you need to translate it to language which will be understandable by your computer. We use compiler for that. And after that, we have output file with binaries, with ones and zeros. But these ones and zeros realistically contain assembly commands, which are really understandable by our CPU. And after that, using these zeros and ones, this binary code, our computer just starting to run our program. But also we need to remember that inside of our computer, we have a lot of cores. And mostly, in common case, every core has a similar structure. So let's take a look a little bit. Typically, we have a lot of units in our CPU. So for example, we have IU, it's integer unit. FPU, it's floating point unit. And we have load storage unit just to send data between memory and registers. Also, we have LU. It's just really basic stuff for our CPU to perform some addition, subtraction operations, and bit manipulations. And we have also decoder in instructions memory. So commonly, when your assembly code starts to execute, it calls some instructions from instructions memory. And after that, all the stuff in your CPU starts to work. So if we'll take a look closer to instructions memory, you can see that there is a comparison just of really small microcommands inside of your CPU compared to your assembly language. So for better understanding, we can say that you have some decoder as API gateway, and instructions memory, it's kind of like black box service, which will do some stuff. So we just send in assembly commands inside to your processor, and after that, something magic comes inside. But if you'll take a look, we know that our processor in common, it's just silicon plate with lots of schema techniques, some logical stuff. And when our microcommand starts to work, a lot of signals inside of our electric circuit on CPU starting to work. Well, inside of our processors, we typically have a heart called clock generator. So with every tick which our clock generator produces, signals on our circuit comes further from previous step to next step, from previous step to next step. So technically, probably you remember these electric circuits you did probably in middle school in physics class. Commonly, we can say that our CPU, it's kind of like the same circuit, but 1,000 times smaller and 1,000 times more complex. So, okay, currently we know that our computer is just contains, in our computer we have some commands memory, we have some circuits, and they need to do some stuff to perform an operations. We have another question, what computer does, and particularly how computer divides. So hopefully 60 years ago, a lot of researchers, scientists, and engineers researched a big amount of methods to perform division inside of our CPU. And most common class of these methods, so-called digit recurrence algorithms. So there are some restoring, non-restoring, and SRT divisions. And SRT division is a typical one for use in our modern CPUs. So it's quite specific one, but it's also about performing bit manipulations, some subtractions and other stuff. And also we have table with dividend and divisor. Just using them, we can predict a last digit of our quotient. It was funny stuff regarding SRT division many years ago. So probably you know first Pentium processors. I hope somebody knows about them. Great. So when Intel released their first Intel processors, what in 1993, they first time used SRT division table for their processor, and probably for some problems at factory, they lost 5 numbers of 1,000 numbers. So that's why prediction of digits in your quotient failed, and you received bad results. I tried to explore something else, and I found that sometimes our computer cannot perform a division. For example, you have a microwave oven in your kitchen, and technically you don't need some blocks which will do some division in your computer, because you just need to subtract minutes, subtract time, or probably add time. You don't need something special. So to handle that, sometimes if you need to perform division in your computer, we can remember some mathematics. So multiplication is the opposite operation for division. And for that, we can use some compile optimization. When I was thinking about it, I found that I can do the same one for my code. And I just compiled my language. I just compiled my program using some compile optimizations. And after that, I opened assembly code for my program. And I found that there is no division operations at all, but we have some strange constants and we have some multiplication inside. So after that, I found that inside of our compilers, there are lots of optimizations regarding division, and it's all about bit masking and some other operations. So we built so-called magic numbers in that case. Even if you will go into documentations for any processors producers, for example, from Intel, you can see that typically they say that compilers will replace a divisor value in some ranges. So does this compile optimization really helps? Yes. So you can see that I reduced execution time of my programs twice if I will use naive division and if you'll use program with division, but using compile optimization. Well, after that, I was just trying to research a little bit more and noticed one interesting thing. So as you know, many years ago, we didn't have so good technical process, and our chips and our computers were really big, but we could not put so much logical elements in our computer. Nowadays, 40 years later, we can put trillions, probably billions of transistors, some logical elements on our silicon plate. So many years ago, engineers had to reuse blocks inside of your CPU. So LU typically was used for simple arithmetics, and floating point unit was about complex arithmetics. So FPU typically contained some divisions, multiplication operations, even square root or something like that. And many years ago, when you ran your program, it probably, if you would work with floating point numbers, you would use FPU. But even if you will do some stuff with integer numbers, you would also use the FPU. But a few years ago, I found that on Twitter. Even architects from Intel telling about that. We have some dedicated blocks inside of our CPU. And even if we will go into documentation of modern processors, we will find that specific blocks are really separated for that. So that was quite interesting for me. Well, what's about the difference? Why we had different results on our Apple CPU and our Intel CPU? Well, first of all, we need to understand that circuits inside of CPU are really difficult and complex, and also it requires some ticks, it requires some time for execute. Also, probably there are some difference in conveyor and some parallelism stuff. And the third one, it's obvious our problem is really simple. So what's about ticks quantity? If you're talking about Intel, it's quite easy for find that because you can read it in specifications. So for Intel, it typically requires from 14 to 47 ticks to perform division operation. But if you're talking about Apple, so Apple is usually close all this information. I randomly found some nice research by enthusiasts, and they performed some benchmarks and found that for Apple Silicon, it only requires 7 ticks to perform division operation. So you can see the difference now. Another one, so it's about conveyor. Modern CPU typically have a conveyor. It means that you can just execute your commands one by one, step by step. And probably there are different approaches for Intel and Apple to perform execution of these assembly commands. And I also found that interesting stuff. I found a person who develops special library to make division in your computer more faster. And this library called libdivide, and he performed some benchmarks on 2 CPUs, an Intel CPU and Apple and 1 CPU. And we can find that if you'll perform some hardware division, in some cases, Apple M1 will be faster than 10 times. I think it's ridiculous statistics. And another point is, our problem is really simple. So typically, CPU in your computer has 64 digits, but if we will just translate 100 million to binary code, it will use only 28 digits. So probably we can use more power of our processor to somehow optimize that. And also, I didn't use some complex instructions. For example, AVX for Intel, it's all about, probably we can make our program more faster using that, but I didn't do that. Well, okay, let's talk about conclusions. First of all, I realized again that division is complex, especially if you're talking about division in our computer. Also, as we now know, individual blocks in processors have been upgraded. If we will talk about reusing them, if we will talk about some optimization inside of CPUs, also we can ensure that mathematics is cool and compile optimizations can really give you much more performance for a program. And also it's about CPUs. So if you're talking about Intel processors, we should understand that the more general the solutions, the more it will be expensive in terms of performance. So I usually receive questions that, so it turns out that Intel processors are worse. Totally not. So of course, they're not so energy efficient, but inside of CPU, we have a lot of any other technologies, for example, hyperthreading, we have AVX and other really complex stuff, which can allow you to make your program more faster and more powerful. And also, if you'll see more closely, typically for Apple processors, it's just different purposes, because usually your Intel chips, your Apple chips used in laptops, used in your workstations, but I didn't see any Apple processors on servers, for example, in data centers. But if you're talking about Intel, it's mostly about using all this parallel stuff to achieve the best performance in many other areas. And just small addition, you can see that if you'll use some libraries or some compile optimizations, difference is not so big in terms of performance for division. So I would say that if you're thinking after that Intel processors are worst, it will be totally wrong. Another question that I usually receive that, okay, you have a CPU and you perform that stuff on CPU, but also you can have a GPU and your graphics card, and graphics cards are extremely fast about computations. So I just rewrote my program a little bit and compiled that for CUDA. It was 3090 RTX, and totally results were great. So you can see initial results using Java language for 15 million was about 64 seconds. Best result for C for 100 million of numbers was 33 milliseconds. And it was less than 1 millisecond using CUDA. I think it's a great result for performing computations on GPU. I guess it's all from my side. Thanks for watching. So probably you have any questions regarding that.
Before you ask the question, raise your hand if I'm forgetting you. Both ask the question. That's the wrong one.
If GPUs are so fast, why don't we just do everything?
Because that was a common question. I was waiting for it. Because typically on your CPU and GPU have different flow of execution. So in GPU, you have so-called simple instruction, multiple data. So GPU has a lot of cores, but it's usually about performing a lot of easy operations. So I mean, you need to load your program on your GPU, of course, but it's all about the same program which will be run. So that's why usually GPU used in very small use cases. For example, for computing your graphics to perform some mathematical operations. But typically, of course, your software usually is run by common use processors. Yeah, so current CPU in your computer can do a lot. I mean, not only these operations, but that's why we have so difficult assembly language here, for example.
Did someone ask a question who didn't get a ticket for me?
Not yet.
I was wondering, like, why did you just do that operation, that mathematical operation? I was just wondering, like, yeah.
It's quite strange. I really was scrolling blind.com, and I really just entered just for lulz FizzBuzz, and after that I tried to achieve some results in Java, and I don't remember anything like that.
Interesting. So basically, the idea was kind of like research and kind of trying to prove work.
Yeah. So in university, I was told that it was kind of like common sense that if you perform addition, it will be faster than division because division is really complex. And I just tried to check it on my computer. And when I got another results when addition was slower than division, I tried to do something with that.
So yeah, what would be your advice when people try to optimize the code so that you start with algorithm or with IO or how to find this bottleneck basically if you want to optimize something also as simple as that as FizzBuzz?
I guess that IO is a well-known bottleneck, so that's why we have a lot of transformation of our input outputs between services, for example, if you're talking about machine-to-machine connections. But I guess that's best one is to use compile optimizations, first of all. And yeah, just think about IO.
Who was this question? Oh, yeah. More questions?
Yep.
Taking this problem, this small-scale problem, so we're using a lot of small operations, and taking into account that most of the processors nowadays have 64-bit architecture, wouldn't it be more efficient to use 64-bit numeric structures, like, for example, in Java, it's long, so that standard buffer for the processor as soon as it is 64-bit would be also 64-bit, and will it increase the...
You're probably talking about alignment. So, for example, if you had 32-digit number and we're working with 64 digits, right? Mm-hmm. Usually, if you're talking about Java, I'm not sure, but I guess now JVM has a lot of hacks for achieving that, and everything is done. So, and regarding this problem, I don't know what can I add.
I'm just not sure how it's working in Java and in C++, but I've tested myself in C#. And the same operation is it was just empty loop where I use first one I use this in iteration variable is integer, so 32-bit value, and it performed 5 million operations per 1 second. And with the long structure, so that it's 64-bit number, it performed 1 billion operations. So it's twice as much because, and I think that it depends on the processor as well. So it connects to your.
It sounds like an addition to your talk when you've done some research.
Yeah. But I hope I'd finished with that, to be honest.
Another question?
Yes, how do you decide to make a comparison between Intel processors and Apple processors? I mean, in the sense of most machines that they need to run like with the sorry, I'm more like like so much on the back of the hardware. So if you're going to need like a CPU to process all the graphic, and you know that's already faster, why did you decide to also test how it's in Apple processors that they don't have any compatibility with GPUs?
So I did GPU just for fun, to be honest. I was comparing just CPUs, and I just wanted to show how we can do these fast operations using GPU.
Okay.
Yeah, so probably I didn't understand your question.
Oh no, it's just like I was just wondering, like if you knew that like with the GPU it's always faster, why do you
it's
like the difference between CPUs? When you don't have compatibility between Apple and most graphic cards.
No, it's just definitely really a specific case made just for fun. So I don't pretend that it will be.
It's that you went so in depth, so I was just wondering, like.
Yeah. So it was really strange, and I just did it for fun.
Actually, another question about like CPU and GPU comparison. So in this less than millisecond computation time to include the time to kind of prepare the data to feed to GPU and get the result back, or it's not included?
Not included. It was just about, it's interesting question. Yes, it's just about execution. So it means that if you're working with GPU, first of all, you need to put your data from your computer memory into your graphics card, execute that, and just take these results. But of course, it will take a lot of time. And that's why I was talking about in one of my slides that we only measure business logic time. We're not speaking about memory allocations and other stuff. Otherwise, it was not so fast, of course.
Well, actually, is it a technical question? I just got graduated from my university. I studied software engineering. And basically what I heard from your presentation today, it's like that question that my math teacher in high school tried to give us as a fun example, 1 + 1 explained by theorems. So basically, you have to go back to all of that hard work in order to finally give an explanation that 1 + 1 is basically 2, and that's all that. But in fact, why I'm saying that is that by what I saw till now, it's how we can manage to put in one simple example my whole degree. So every single module I got to study through 3 years, I got to see in a simple example. So my question is, can I borrow it and maybe bring it out, or I would invite you to bring this out in a small interview in order to give your work as a model for young students.
Yeah, feel free to contact me, and yes, you can just take his presentation. You can see this QR code.
Great job.
So there's a question here?
My question was like, your conclusion are based only on the executing the same task in both CPUs, April and.
Yep, it's just really particular, only one example that I just try to computate everywhere.
Maybe what function will be the same your test, execute another test, or it may change?
To be honest, I guess we will get different results for different purposes on Apple and Intel CPUs. So it's just only about division. And in the link, to be honest, this link is quite interesting for me because it's all about, just let me find that. Just one sec. Okay. Great. This one, yeah. Probably there is a schema. It's a quite interesting one because it's about how your CPU really works. And it's all about some latencies inside of your CPU. So I guess if you will find the same one for Intel processors, for example, I also have a link in my presentation. We will have different results for different blocks who will work with that. So
yeah. Depends kind of what low-level methods or library stuff you're using for the specific algorithm challenge at hand, I guess. It's what you're influencing because as you're saying, it's utilizing different parts of the architecture.
Yeah.
One last question, maybe? Okay. Yeah.
Have you also tried AVX or some other CPU-based symphony instructions to compare to the GPU-based symphony instructions? I'm kind of curious of how the CPU-based versus GPU-based symphony is comparing it.
to be honest, I decided to stop at this point. So I didn't try. Probably in future I will do that. It's quite interesting because AVX is also SIMD. But I guess it's more smaller, of course, because we have so much cores in GPU and we will get real different results. But we can just compare Intel CPU without AVX and with AVX. It will be quite interesting, I guess. You can take a source code at least.
Thanks.
Thank you.